Hey y'all, so let's cover 3.3. Remember with constant rate of change that was given 2 points, we were able to find basically the rise over the run for a line. Well, now we're going to talk about many different things, not pertaining to just a line, but say choosing two arbitrary points in time as we go through and finding out the rate of change between when those two things happened. Or what those two things did when it happened. So let's start with example one. I'm just going to jump on into it so I can show you how to work through these. All right, example one, find the average rate of change of the price of gasoline between 2005 and 2008. Okay, so that's just looking at 2005, the cost was $2.31. 2008, the cost was $3.30. So we already have, it looks like, two ordered pairs that we can do here, and that's 2005. Remember, time is always your independent variable or your X variable, 231, and the other one is 2008, 330. All right, so I'm going to just use the same y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And when you do that, I'm going to label these real quick, x1, y1, x2, y2, 330 minus 231 over 2008 minus 2005. Well, that's 3 years. Let me see what the other is. I do not have my calculator in front of me, so bear with me. Actually, let's do it here. It's great. 330, 231. 99 cents. So 99 cents per 3 years. So that reduces, if you divide 3 into 0.99, that gives you 0.33. So the average rate of change of the price of gas between 2005 and 2008, let's put that in there because time is nice to have, 2005 and 2008 was dollar signs to represent the units. And then you can't see a thing I'm writing, so that's even better, 33 cents. All right, that is your answer for that one. Moving on. If you have any questions, please make sure and make note of it and let me know so I can help you. I'm happy to do so. So given the function g of t, we've talked about this before. If the function itself is making you kind of crazy and you're like, I don't like g of t, then change it to f of x. It doesn't matter. Just make sure and represent it here as well as down here being an x instead of a t. So we're going to look at finding the average rate of change on the interval. Now, this is an interval, so this is basically looking at what a restricted domain would be. And we'll talk more about that here a little bit later. But this is both having to do with the x values or the t values. So between -1 and 2, what is happening? What's the rate of change? Well, first you need to know where -1 is on this. Oh, good gracious. I'm going to say it's possibly 3, and then 2 looks to be about 1. So we've got two ordered pairs here. We've got -1, 3, and we've got 2, 1. So we're going to find the average rate of change on the interval between these 2 points. The interval is from -1 to 2. So x1, y1, x2, y2, and we're going to do y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Y sub 2 is 1 minus y sub 1 is 3 divided by x sub 2 is 2 minus x sub 1, which is -1. So 1 minus 3 is -2 over 2. Negative times negative is a positive. So 2 plus 1 is 3. Is that what we had earlier? Sure. So our average rate of change from -1 to 2 is -2/3. Okay, moving on. All right, I could have used different points in class because I cannot see this as well. All right, so let's look at example 3. After picking up a friend who lives 10 miles away and leaving on a trip, Anna records her distance from home over time. find her average speed over the first 6 hours. So we need to look at the 0 hour and the 6th hour, and those are going to be our ordered pairs. Remember, time is our independent variable. So it is going to be in our x value, and our dependent variable will be our function, of course, d of t, and then 6 and 292. I'm going to go ahead and order, label the order pairs x1, y1, x2, y2, and then we're going to go y sub 2, how much space I have, minus y sub 1 over x sub 2 minus x sub 1. Y sub 2 is 292, minus 10 is y sub 1, over x sub 2 is 6, minus x sub 1, which is 0. So that's 282 divided by 6. I thought that was 47 or something. Let's see, 282 divided by 6. Oh, well, those stinkers. I could have sworn they said that was a perfect number. It is not. But it reduces. That's very frustrating. So it gives us a decimal, so the decimal would be 4 point, let's just say 67. And what is this? This is the average. This can't be right. That can't be right. Hold on. 282 divided by 6. Oh, that's what it is. 282. Stinker. I'll say that's good. There we go. It is 47. I'm so sorry, y'all. My clicking was wrong. It's 47. All right, so that makes much more sense. I'm like, that's so weird. So the average speed over the first 6 hours. So the average speed over the first 6 hours was 47, and it's miles per hour, mph. All righty, let's move on. Sorry about that little blooper. Don't want that anymore. Get rid of that. Example 4, compute the average rate of change from the function f of x is equal to x squared minus 1 over x on the interval. So that's between where the domain or the x values are between 2 and 4. Those are both x values. So the first thing I'm going to do is find f of 2. And that's just 2 squared minus 1 over 2. All right, which is, I'll just go up here, 4 minus 1/2, which is 3.5. Trying to decide if I wanted to leave this into decimal or not. F of 4 is equal to 4 squared minus 1 over 4. So that's 16 minus 1 over 4, which is 15.75. Okay, so now we've got 2 ordered pairs. The first one is going to have the x value as 2 and the y value of 3.5, which is our output from plugging 2 into the function. And then the second value is from the 4 in the domain, and it's representing 15.75. All right, so now we can use y sub 2 minus y sub 1 over x sub 2 minus x sub 1. I'm going to go ahead and label my ordered pairs. Oh, that's 2. All right, 15.75 minus 3.5 divided by 4 minus 2. Well, that's 2. And what is that? 12.25, it looks like. Yeah. Okay, so that's 6.125. Yeah. All right, so the average rate of change on the interval, average rate of change from 2 to 4 is, there you go. Moving on. Electrostatic force, F, measures in newtons between two charged particles can be related to the distance between the particles, d in centimeters, by the formula. This is our function. F of d is equal to 2 divided by d squared. Find the average rate of change of force if the distances between the particles is increased from 2 to 6 centimeters. So we're just going to find the values of the function at 2 centimeters, and then we're going to find the value of the function at 6 centimeters. And then that's going to give us our 2 ordered pairs that we can find the rate of change from. So at 2 centimeters, I'm just going to take 2 and plug it into where the d is. So 2 divided by 2 squared is 2 divided by 4, which is 1/2. The other one is 6. So 2 divided by 6 squared is 2 divided by 36, which is 1 over 18. I remember in class, I left this in fractional format and it worked out really nicely. And hopefully I can help some of y'all a little bit better with your fraction work. So now we've got two ordered pairs. We've got 2, which gave us 1/2. And then we have 6, which gave us 1 over 18. Y sub 2 minus y sub 1 over x sub 2 minus x sub 1. I'm going to label my ordered pairs. X sub 2, y sub 2. So 1 over 18 minus 1/2 over 6 minus 2. Well, the bottom one's easy. That's just 4. The top one, in order to subtract these, we need to have a common denominator. So in this case, it's going to be 18. This one already has 18, so we don't have to do anything to it. The other one needs to be multiplied by 9. What we do to the bottom, we do to the top. 2 times 9 is 18, so this one's good to go. So this one becomes 9. So we've got 1 over 18 minus 9 over 18 over 4 is where we're at. Okay, I'm just going to bring this down here. All right, so this gives us 1 minus 9 is negative 8 over 18 divided by 4. When you have a fraction division, I'm going to come over here and show you what that looks like. That's just negative 8 over 18 divided by 4. And I've been told that in school they teach y'all the keep, switch, flip, to where you keep the first fraction, you switch the division to multiplication, and then you flip the 4 to 1 over 4. You just do the reciprocal. All right, before I want to multiply across, I just want to reduce this real quick because I hate big numbers, and 18 times 4 is going to be big. 8 and 18 will reduce by 2, and that will give this one a 9 and this one a 4. And then these 4s reduce, so this becomes a 1. It's a negative 1. Negative 1 times 1 is negative 1, and then 9 times 1 is 9. So the average, what is it? The average rate of change of force. We're done. Yep. The average rate of change of force. I'm just using their words. It's just easier. If the distance between two particles is with particles increasing from 2 to 6 centimeters is negative 1/9. Okay, and that is our answer for that. Right, moving on. Find the average rate of change of the function g of t is equal to t squared plus 3t plus 1 on the interval from 0 to a. Okay, so first thing we're going to do is find the two ordered pairs, which is what we've been doing so far, given that our domain or our x values are 0 and a. Okay, so we're going to start with the function g of 0. G of 0 is delightful. It's just 0 squared plus 3 times 0 plus 1, which is just 0 squared is 0 plus 3 times 0 is 0 plus 1 is just 1. So our first order pair is 0, 1. Our second order pair is going to be a, and then whatever that comes out to. So g of a is just everywhere there's a t, we're now going to have an a. So it's, oh, I did leave myself enough room. A squared plus 3a, I'll do that, plus 1 is my second order pair. All right, so now I can use my rate of change, x sub 1, y sub 1, x sub 2, y sub 2. So I'll go y sub 2 minus y sub 1 over x sub 2 minus x sub 1. I'll come over here. Y sub 2 is a squared plus 3a plus 1, and then minus y sub 1, which is 1. Just separated that with parentheses just so that you can see that it's y sub 1 is being represented. You didn't have to do that. And then x sub 2 is a minus x sub 1 is 0. So that is a squared plus 3a over a. Now there's two different ways you can handle this. I showed it two different ways in class, at least in the class in fall 23. is you can, my first thing is I see I can factor out an A from the numerator, and that gives me A plus 3 over A. Then these A's reduced and you're left with A plus 3. That's the final answer for this one. All right. The other way I showed this was you could take this, hopefully that wasn't important. You could take this part of it and break it up to A squared over A plus 3A over A. My only issue in showing this is because I find when folks do this, they only put this A underneath one side, and that's not right. So this reduces to A squared divided by A is A, and then 3A divided by A, these reduce and give you plus 3. You have to put that A underneath both, or however many is there. All right, moving on. Use the graph to determine where a function is increasing, decreasing, or constant. So if you think about this as a roller coaster, which is how I explained it in class, and you're reading, like we read everything else, we're reading it from left to right, right? So left to right, as we're coming along, if you were to hit this on a roller coaster, you're going up, okay? So this has to be increasing because it's going up. And then you're going to hit a point right here that is neither increasing or decreasing, okay? From that point, that's called a turning point, now you're decreasing, okay? So as you're heading south, you're decreasing, and then you're going to hit another turning point here, and then you're increasing again, all right? So if we're looking at these as intervals, we are increasing. So I would write this as an interval, not as an ordered pair, as an interval. It's increasing because it's coming from negative infinity. It's increasing up to -2. -2 is never included. With this is increasing. It's also increasing from 2 to positive infinity. So it's increasing here. It is decreasing from -2 to 2. And that is it. Okay. All right. Local min and max. So in order to have a local max, you have to start off from left to right, be increasing and then decreasing to have a local max. So we're increasing and then decreasing. That is a local max. All right, it's the highest point from an increasing side. Then if you look at for decreasing, I'm looking for the lower, the local min, the minimum, you have to be decreasing and then increasing. You have to have those happening in order to have your local max and min. Okay, so I want to do a couple of things here. Is this like the last one we just did? Yep, it's just like it. Okay, so you could say the local max occurs at x equals -2 and is 16. You could say the local max occurs at 2. Our local min occurs at 2 and is -16. Or you can label them in order pairs as they are represented here. Okay, so you've got several options of things you can do. All right, last one on this part. It says, given the function, identify the intervals on which the function appears to be increasing. Okay, so going left to right, the second, I know the arrow is pointing up, that does not mean it's increasing. Okay, it's actually decreasing as we're coming left to right. Decreasing, then it hits a turning point, then it's increasing, hits a turning point, decreasing, hits a turning point, and then increasing again. So if we're going to say what these are increasing on, it's increasing on the interval from 1, I'm sorry, let's do 1 to 3, and then from 4 to infinity. Okay, we're not going to do, all right, and then the other one is decreasing, let's just go ahead and do that, decreasing from -infinity to 1, and then also from 3 to 4. Okay, all right. Finding local extrema from a graph. Graph the function f of x. Okay, I need to graph that. Hold on 1 second so I can show you what it looks like. Bear with me. I'm going to pause. Okay, this isn't exactly my favorite graph, but one of the things I do want to show you is something interesting. Because I told you earlier, and this is the graph that was on example 8. I wanted to show you it on Desmos just because it's nicer. If we talk about local min and local max. So remember when I said you have local max, the first thing people want to do is come up here and say, okay, this is my local max. It's 2.5, 1.6. And the problem with that is local max, you have to be thinking about a roller coaster that you're going up to the top of the max and then you turn and you drop back down. Well, that's not what's happening with this one. So we need to come down here, and in this part of the function, we're going to go, it's increasing and then it's decreasing. So this is where our local max is going to be. Up here, it's decreasing and then increasing. So this is where our local min is going to be. All right. I have a few more that I want to go over. And then, yeah, just to make sure that you have that. So let me move things back around again. Give me just 1 minute. There we go. All right. So now coming back to, oh, this is the actual picture. I'm going to come down to example 9 because I had you do this one in class and I wanted you to find the increasing, the decreasing, and then the local max and local min. All right. So local max, okay, let's find the increasing and decreasing first. Increasing, well, this one's coming down. So that's decreasing. And then this one's going up, so that's increasing. And then we're decreasing again. Okay, so we've got turning points here and here. So decreasing is going to be from negative infinity to -1, or from 1 to positive infinity. Increasing is happening between -1 and 1. All right. The local max, we have to be going from increasing to decreasing, and that's happening at x equals 1, and that is 2. So we can put 1, 2. And then the local min happens when you're going from decreasing to increasing. So decreasing to increasing happens at -1, and that is going to be -2. All right. Toolkit functions, just to help you see some other things. And then I'm going to stop the video and then I'm going to do 3.4. Good times.